Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the generalized enthalpy departure chart. We have mentioned many times gases at low pressures behave as ideal gases and obey the relation. The properties of ideal gases are relatively easy to evaluate since the properties depend on temperature only. At high temperatures, however, gases deviate considerably from ideal gas behavior, and it becomes necessary to account for this deviation. We have accounted for the deviation in properties P, V, and T by either using more complex equations of state or evaluating the compressibility factor Z from the compressibility charts. Now, we extend the analysis to evaluate the changes in the enthalpy, internal energy, and entropy of non-ideal gases using the general relations of du, dh, and ds developed earlier. The enthalpy of a real gas in general depends on the pressure as well as on the temperature. Thus, the enthalpy change of a real gas during a process can be evaluated from the generalized relation equation 541 for dH. For an isothermal process, dt equals 0 and the first term vanishes. For a constant pressure process, dP equals 0 and the second term vanishes. Using a superscript asterisk to denote an ideal gas state, we can express the enthalpy change of a real gas during process 1 to 2 as 1 to 1 asterisk to 2 asterisk to 2 as shown in the right figure. Recall that properties are point functions, and thus the change in a property between two specified states is the same no matter which process path is followed. This fact can be exploited to greatly simplify the integration of equation 541, taking process 1 to 2 as the example. The enthalpy change from 1 to 2 can be divided into 3 parts. The first part is that from 2 asterisk to 2. This is an isothermal process. Equation 541 can be simplified as. The second part is that from 1 asterisk to 2 asterisk. This is an isobaric process for an ideal gas. Equation 541 can be simplified as. The third part is that from 1 to 1 asterisk. This is an isothermal process. Equation 541 can be simplified as. The difference between H and H asterisk is called the enthalpy departure, and it represents the variation of the enthalpy of a gas with pressure at a fixed temperature. The calculation of enthalpy departure requires a knowledge of the PVT behavior of the gas. In the absence of such data, we can use the relation where Z is a compressibility factor. Substituting, we have the enthalpy departure can then be obtained by integration the above expression. The preceding equation can be generalized by expressing it in terms of the reduced coordinates using T and P. After some manipulations, the enthalpy departure can be expressed in a non-dimensionalized form as, where ZH is called the enthalpy departure factor. The integral in the preceding equation can be performed graphically or numerically by employing data from the compressibility charts for various values of PR and TR. The values of ZH are presented in graphical form as a function of PR and TR in figure B7. This graph is called the generalized enthalpy departure chart, and it is used to determine the deviation of the enthalpy of a gas at a given P and T from the enthalpy of an ideal gas at the same temperature. Therefore, for the enthalpy change of a gas during a process 1 to 2 can be rewritten as, where the values of ZH are determined from the generalized enthalpy departure chart, and this term is determined from the ideal gas tables. Notice that the last term on the right-hand side is 0 for an ideal gas. With the generalized enthalpy departure chart, as long as the critical temperature and critical pressure of the fluid and the enthalpy at the same temperature in the ideal gas state are known, the enthalpy value of the actual gas can be obtained. Okay, that's all for this task. Thank you very much and see you next time.